All right, everyone. Hello, and welcome to the screencast in which we're going to learn how to calculate the probability of a Condorcet vote cycle. So if you don't know what a Condorcet vote cycle is yet, you need to go back and watch the previous couple of screencasts because we're just going to kind of jump right on in, assuming you know what that definition is. I will show you one brief example before we calculate the probability, though. All right, so well, what if there is no vote cycle? You've already heard some of this vocabulary, but I just wanted to remind you that when pairwise majority rule leads to an outcome, we call that outcome the Condorcet winner. So a Condorcet winner is an alternative that cannot be defeated using pairwise majority rule. All right. So that means if you're running pairs of things together, there's something that beats all the other alternatives. All right. It can't be defeated. All right. All right, so in general, what does an example of a Condorcet vote cycle look like? Well, here's a general form of the Condorcet vote cycle, and if you ever have to recreate one of these with three people and three alternatives, notice that I have person 1, person 2, and person 3, and I just went A, B, C, A, B, C, and then A, B, C. This particular preference profile for these three individuals is actually guaranteed to cycle. And as a reminder, here's what that looks like, all right? So if I run alternative A against alternative B, right? So I'm looking at all the cases for how many of these people does A defeat B, and for how many of them do they prefer B to A, I should say. So if I run A versus B, well, person 1 prefers A, person 2 prefers A, and person 3 prefers B to A, right? So A wins 2-1, all right? Again, if you didn't follow that, go back and watch those previous screencasts. We do it a lot slower, but for now, I just want to remind you. So what if I then run B versus C? Well, person 1 prefers B to C, person 2 prefers C to B, and person 3 prefers B to C. So B gets 2 votes, alternative C gets 1 vote, and so so B beats C. What about with C versus A? Well, with C versus A, here person 1 prefers A to C, person 2 prefers C to A, and person 3 prefers C to A. So C wins. All right. So this is a Condorcet vote cycle. All right. So the group's preference ordering is the group prefers A to B, the group prefers B to C, but then the group prefers C to A, causing the vote cycle, all right? And so this is an intransitivity. A Condorcet vote cycle means that the group's preferences using pairwise majority rule are intransitive, even though individually they each have transitive preferences, okay? So using pairwise majority rule, this set of preference profiles will cause a cycle. But notice, this was just 3 of the possible preference profiles that people could have, right? Person 1 prefers A to B to C, person 2 prefers C to A to B, person 3 prefers B to C to A. But as you've seen in some of the previous screencasts, we could have a situation where each of them all prefer A to B to C, right? So there's lots of different possible 3-person, we're going to call them societies, that some of them might cycle, right? This one cycles. But then others of them, for example, again, let me create that one here just to be specific, A, B, C, A, B, C. So here they all have the same preference profile, and if I run this tournament here, then we're going to find that A is always going to win. It's always going to be the group's choice, and their overall group preference will not cycle. All right, so the question we're asking in this screencast is, how likely is it that we will get a cycle? All right, so individuals can prefer one outcome to another, or they can be indifferent, right? So between A and B, they can have a strict preference, person I here, between A and B, or they can prefer A to B, right? So we're going to look at person I here. We're going to look at all the different ways that a person, so let me go ahead and put C in here too. So this person prefers A strictly to B, B strictly to C. This person, I'm going to make them indifferent between A, B, and C. So there's 2 possible preference orderings that any given person could have. But of course, there are others. Someone might prefer A strictly to B, and then be indifferent between B and C. That's another possible preference profile. So what we want to do is get a sense of what is the total number of these preference profiles, and then out of all those possible preference profiles, how many might cycle. And we'll do that in steps, okay? So if we have a set of alternatives, A, B, and C, they can be ranked in 13 different ways. All right, I showed you 3 of them just now. Right here, there are 3 of the 13, but there are actually 13 different ways. So I'm going to move from this to more of a chart, all right? So here are all the ways that you can order 3 alternatives. A is strictly preferred to B is strictly preferred to C, right? Here is another possible preference profile someone could have. A is strictly preferred to C is strictly preferred to B, right? And so forth. These are all the strict preferences. In this case, number 7, if a person has this profile, then they are indifferent between A and B, and they strictly prefer A and B to C. So for this one, the 7th preference ordering here, if we drew that in our preference notation, person I is indifferent between A and B, but they strictly prefer A and B to C, all right? It doesn't want to let me put a dot on the I. There we go, all right? So that's what this 7 means. This one here, preference ordering number 13, is the person is indifferent between A, B, and C, person I is, all right? So that's how you read these. So there are 13 possible preference orderings for 3 alternatives. So that's step 1, all right? And actually, we're going to simplify this in a second, but let's keep going here. So a person can have any one of these. So an individual, if I asked them to rank A, B, and C, they would pick one of these preference orderings, all right? So let's think about how likely cycling is. So how many combinations of these orderings could 3 people have? So we're going to first look at how likely is it to get cycling when we have 3 alternatives and 3 voters. All right, so that's what we're going to look at. 3 alternatives, 3 voters. With 3 alternatives, we know that you can have 13 different orderings for 3 alternatives. And then for 3 voters, that means we might have voter 1 has this preference, voter 2 has this preference, and voter 3 has this preference. All right, that's one possible way we could have it, all right? So that's the game we're going to play here, all right? So it turns out that how many combinations of orderings could 3 people have? Well, there are 13 possible preference orderings, and if there are 3 people, then that gives us 2,197 different societies. We're going to call that a society, all right? So when 3 people walk up to this list of orderings and they pull their orderings, that's a society, all right? So these 3 I circled here is one society. Another society might be, what if they all 3 have this preference ordering? That's another possible society. Another society here might be if one person has this ordering, another person has this ordering, and the third person maybe has this same ordering. That's another society, all right? So it's all the different combinations of these orderings is what we're after, and it turns out that's 2,197 different societies. And so our question is going to be, how many of those societies would cycle, right? Because we know, for example, that in this case, we do get a cycle. This is one society, one possible society, all right? And this one does cycle. But then this case, where they all have the same preferences, for this society, it doesn't cycle, all right? So we're going to look at that. Yeah, so here's one possible society. A is strictly preferred to B is strictly preferred to C. This is the one where they all have the same exact preferences, all right? So to simplify this a little bit, we're only going to consider the strong profiles in order to make the calculations a little bit easier. So when I ask you to calculate the probability of a Condorcet vote cycle, you're only going to be looking at the strong profiles. That means no indifference is allowed, all right? So no indifference. So of those 13 different orderings, all right, there are 6 of them where there are no indifference. So we're going to just, when we calculate the probability of a cycle, we're just going to get rid of these and calculate this. Because what we really want to see is if we increase the number of alternatives, are we more likely to get a cycle? And if we increase the number of people, are we more likely to get a cycle? And to answer that question, we don't really need to have all of these weaker preference profiles. So we're only going to look at these, and that's going to simplify things a good bit for us, all right? So for 3 alternatives, right, we have A, B, and C, 3 alternatives, and if there are so for 3 alternatives, there are 6 possible preference orderings. 1, 2, 3, 4, 5, 6. So those are the 3 different ways that you can have strict preferences over 3 alternatives. So it's 6 possible orderings with 3 alternatives means there are 216 possible societies here. All right. So how many of those 216 societies would cycle? All right. So it turns out that 12 out of the 216 would produce a cycle. And I'll give you this number. I'll tell you how many of them will cycle. All right. So that's not too bad, actually. Look, only 12 out of 216 possible societies would cycle. That's not bad. We're very unlikely to get a cycle here. All right. So 204 of 216 possible societies with 3 alternatives have a Condorcet winner. So we're very likely for any random society of people with preferences over 3 alternatives, we're very likely to get a Condorcet winner with 3 people, okay? So small number of people, and we have a small number of alternatives. Pairwise majority rule is going to work fine most of the time. You're not going to get that Condorcet vote cycle. You can't be sure, it can't be guaranteed because there are 12 of them, 12 of those strong orderings that do produce a cycle, right? And remember, the one we've been using is where person 1 prefers A to B to C, person 2 prefers C to A to B, and person 3 prefers B to C to A. This one is one of these 12. It will cycle, as we saw at the beginning of the screencast, all right? So what happens if we start to increase the number of people or we increase the number of alternatives? All right. How likely is cycling then? So we're going to call N, right, the number of individuals, and M is going to be the number of alternatives. And if you have that, then you can calculate the probability of a vote cycle. You use this formula, all right? So all this says is that the probability of a vote cycle when you have M alternatives and N voters equals the number of societies that cycle, and I will give you this, that's why I have it highlighted in green here, to remind myself to tell you I will always give you the number of cycling societies, all right, over M factorial to the N, all right? So if you don't recall what your factorial is, all it is so if M here, well, let me just give an example of 5, right? 5 factorial is just 5 times 4 times 3 times 2 times 1. Don't multiply by 0, right? Because that would be 0. But that's all this notation means. So 5 factorial means 5 times 4 times 3 times 2 times 1. So if you have 4 alternatives, then you would plug in right here 4 times 3 times 2 times 1. All right? You get the idea. We'll do an example in a second. And then you just take it to the power of the number of voters. So again, I'm just repeating this formula here. The probability of a vote cycle given M alternatives and N voters equals the number of cycling societies, which I would give you, over M factorial to the N. Okay? So for the probability of a cycle when you have 3 alternatives and 3 voters equals, I told you that there were 12 of them, 12 cycling societies, again, I'll give you that, is 3 factorial to the 3rd. So 3 factorial equals 3 times 2 times 1, which of course is 6, and then 6 to the 3rd power equals, what is it? I wrote it down somewhere, 216, all right? So the denominator here is 216. So we get 12 over 216 equals 0.056. So the probability of a vote cycle with 3 alternatives and 3 voters is 0.056. It's a really, really, really low probability. All right, it's a 5.6% chance. It's really low. You can, and then if you look at table 4.1 on page 58, it shows the probability of a vote cycle for all sorts of values of m and n. All right, so first it takes, and it says, okay, let's add one alternative, calculate the probability of a cycle. Let's add another alternative, calculate the probability of a cycle. Then it goes back and does the same thing for the number of voters. And then it does all the different combinations of the two. All right, so what you'll see when you look at that is that as the number of alternatives goes up, then you almost certainly get a cycle. So the bigger problem, well, let me finish this. And then as the number of people increases, it also makes cycles more likely, but not quite as much as the number of alternatives. So when you're worried about, is it possible for me to get a Condorcet vote cycle, the more alternatives you have, the more likely it is you'll get a cycle. All right. The more people, it does make it more likely, but not as quickly as the number of alternatives. And again, if you check that table 4.1, you'll see exactly what I'm talking about there. So unless a group is small, and more importantly, the number of alternatives is small, then you'll probably get a vote cycle. It's likely that you will, indeed. All right. So we need institutional mechanisms for keeping participation restricted and a way to weed out some of the alternatives. All right. So if we can restrict the number of choices and restrict the number of voters, then we're less likely to get a cycle. Of course, neither of those things makes us very happy when we're thinking of democratic processes, right? Because we want everyone to vote, and we want them to be able to vote over whatever they want to vote over. That's true, but if in those cases, you're very likely to have a situation where there would be a vote cycle, all right? So with majority rule, we're going to have to tolerate one or more of the following things, all right? We're either going to have group incoherence or intransitivity. We're going to have to tolerate the chances that we'll have a vote cycle, or we're going to have to restrict who gets to vote, or we're going to have to restrict what is allowed on the agenda, meaning what is allowed in the choice set, meaning small m, okay? So those choices don't make fans of democracy very happy, but you have to pick one of these things, right? You're either going to say, I want everyone to be able to vote over whatever they want, and I'm okay with the possibility of a vote cycle. Or if you definitely don't want a vote cycle, you want to make sure there's no intransitivity in the group preference ordering, then you have to restrict the number of voters, or more importantly, restrict the number of things that are allowed to be voted over. All right? Okay.